Okay. So today we're going to see the connection from sigma notation into and merging that with Riemann sums and getting to something that is, well, we're going to involve the limits to essentially find the exact area of the curve. But before we do that, though, I want to go through one of the homework problems that you guys did. This is on page 8 in your packets. You may have done 29 on a separate page, or you may have done it directly on page 8, which is fine. But I do want to kind of go through this problem in detail and just to kind of see what, yeah, it's going to be a good preview into what we're going to want to achieve on the next page. Okay. Right, so the purpose here, we're trying to find the left and right endpoints. So we're going to find two approximations: left-handed rectangles using left-handed rectangles and right-handed rectangles. Okay, so first thing we do is we're going to go ahead and find the width. So our width formula is b minus a over n. Right. Our a value is 0, our b value is pi over 2, and our n value is 4. Okay. Okay, so pi over 2 divided by 4 is same thing as pi over 2 times 1/4, which is same thing as pi over 8. And so pi over 8 is our width. Right? And then from the width, we're going to be incrementing that width from the left endpoint all the way until we reach pi over 2. So the graph looks something like this. Right? And then to do left-handed rectangles, we don't necessarily have to know what the graph looks like. We're just always purposely trying to find each of the intervals and then choose the left endpoint of each subinterval. So we know we're going to start at 0. And we're going to keep incrementing by pi over 8 until we reach our endpoint. So plus pi over 8 is pi over 8. Plus pi over 8 is 2 pi over 8, which is pi over 4. Plus pi over 8 is 3 pi over 8. And then plus pi over 8 is 4 pi over 8, or pi over 2. Okay. If I want to do left-handed rectangles within each subinterval, I want to choose the left endpoint to attach to the curve. So I'm going to start at f of 0, which will represent the height of my first rectangle. Second rectangle, I want to choose pi over 8 to represent my height. Third rectangle, I want to choose pi over 4 to represent my height. And then the fourth rectangle, I want to choose 3 pi over 8 to represent my rectangle. Okay. So then if I want to find the area, the width of my first rectangle is pi over 8. The height of my first rectangle is f of 0. And f of 0, it just represents how I'm going to find the height. It's not the actual height value, but it does tell us how to do it. We're going to insert 0 into cosine to get that value, and that's going to be our height. And then second rectangle, pi over 8 times f of pi over 8, because f of pi over 8 represents the height of my second rectangle. Now, we could factor the pi over 8 out. I'm just showing the width and height for every term for now. Third rectangle, I want to choose pi over 4. Fourth rectangle, I want to choose 3 pi over 8. And then now we're going to insert 0 into x of the function and get that decimal value, and that decimal value will represent the height of each of my rectangles. Okay, by the way, this is we're starting off with left-handed rectangles. Okay, plug power 8 in for cosine of x, or in for x of the cosine function, and that decimal value ends up giving us 0.924. Power 8 times f of power 4, plug power 4 into the function, I get 0.707. And then 3 power 8 into the function gives me 0.383. That's all using the calculator to get our decimal value. And then if we just total all that together, we get 1.1835. And that will represent left-handed rectangles. And also in this case, we can also call this what? Upper rectangles, right? Now, left-handed rectangles is not always going to guarantee an upper rectangle just because the graph is always decreasing. And so we can also categorize it as upper rectangles. But the purpose here is just to use left-handed rectangles. It doesn't care about whether it's upper or lower. Okay. And then if I want to do a right-handed rectangle, I'm just going to do a shortcut here. Factor out the power of 8, the width is going to be the same, but then rather than choosing the left endpoint, I'm choosing the right endpoint of each subinterval. So I'm going to start at power of 8 because power of 8 is the right endpoint of my first subinterval. Then I do power of 4, then I choose 3 power of 8, and then I choose power of 2. Okay, and then that will give us an area of 0.7908. This is going to also end up being a lower rectangle, or lower sum, because the graph is always decreasing, so the left endpoint will always produce inscribed rectangles. So it makes sense that this value is smaller since this is under approximation. This also happens to be an over approximation. Okay. So before we get to the next page, we're going to explore a formula that's going to help us move towards an exact area of the region. But I want to kind of show us all the things that the formula is going to do on the next page. Okay, it's going to look really messy because it's going to try to do a lot of things all at once. Okay, so just want to kind of point out all the things that we did by hand that is going to be put into a formula. Okay, so the first thing is the formula is going to do the job of finding the width. Okay, now the width is going to be represented in terms of n because we're going to have a flexibility to change the number of rectangles as we move towards exact area. Okay. Second, it's going to do the job of the next formula on the next page. It's going to do the job of incrementing from the left endpoint the width of each subinterval. Okay. So we add a power of 8 every time, but the formula on the next page is going to do that work for us. Okay. And then after it finds each of the subintervals, it's also going to plug each of these endpoints, each subinterval endpoints into the function to get the height component. And then it's going to take each of those decimal values and add it to the width and then formulate the area. Okay, so it's going to do all those 4 things all at once, all within a function. All within the formula. So that's why it's going to look so complicated on the next page. Okay, so I'll come back to this and kind of point out what the formula is doing on the next page as we get to it. Okay, so I want to kind of point that out before we get to it. Okay, so now let's go to page 9. Okay, so far, we've just been using relatively few rectangles to approximate the area, right? 2 or 3 or 4 rectangles. But the idea here is that we can continually improve the area approximation under the curve if we increase the number of rectangles, right? So let's say we're taking this region and using 4 rectangles. I mean, it's not a bad approximation, right? Looks like it'll kind of give us an idea what that area is. But you can see that there's quite a few gaps that's not matching exactly what the area is. But if we were to use a more number of rectangles, we see that if we use more rectangles, the smaller rectangles will adapt to the sudden changes of the curve a lot better. There's still gaps, but we can definitely tell there's less gaps. Right? So imagine if we were to take approximate this region using more rectangles, like 16 or 32 or 100, the approximation should get better and better. Right? So then what if we take that idea and say, well, what if we have infinite number of rectangles? Okay, so if we let n go out to infinity, if we have infinite numbers of rectangles, we should be able to do something better than approximation, right? It should help us approach the actual area under the curve. So that is why we're going to bring in limits, because we're going to take n, the number of rectangles, and we're going to push it out to infinity. And if we do that, then we should be able to approach not only a very good approximation, it should lead us to the exact value. And that is why we started Wednesday talking about limit as n approaches infinity, because we're going to use that concept of comparing degrees to help us reach where we want to go. Okay. So here is the area formula that we're going to be using. You can see that it looks really complicated because it's holding on to that n variable because it wants to push it out to infinity. So we're going to have to hold on to a bunch of n values across the formula, right? We don't want to just let n be 4 or 3, then it's kind of stuck. We want to let n have that flexibility to move out to infinity. So this b minus a over n is the width component, okay? And we use the width component on the previous page, right? B minus a over n. And then this is where the complicated part is. This is the height component, okay? So let's say, remember the width on the previous page was pi over 8, right? And then what we did was we found that pi over 8, and then we took that pi over 8 and we added it to the left endpoint. So we did 0 plus pi over 8 plus pi over 8 plus pi over 8. And then the first plus pi over 8, it's going to take that first sub interval and it's going to take that value and plug it into the function. So that's what this is doing. Okay, it's taking that first height, plugging it into the function, but then immediately after that, it's incrementing to the next subinterval. So pi over 4, for instance, and then plugging to the function. But it's doing that all at once within this little formula here. Okay. So this is kind of self-automated. It's going to do all that work for us. We just have to set it up and then get it cleaned up using our summation formula and our limit notation. But all the pieces are here, right? You got the width, you got the height, and we're basically adding infinite numbers of rectangles because all rectangles have a width and height component multiplied together. Okay. So I'm going to be giving you this formula to use on the quiz, but we just have to know how to use it. Okay. All right, so example 1, find the exact area between the curve of 4 minus x squared and the x-axis from -2 to 2. So the graph looks something like this. We don't necessarily have to worry about what the graph looks like. But we're going to be using infinite numbers of rectangles to find the exact area of that region. Okay, so this is how we start the process. Okay. We're going to start inserting into the parts that we can do. So what's our A value? -2. What's our B value? 2. Okay. And what's our N value? Yes, we're going to leave it as N, and eventually we'll push it out to infinity. So we're not going to have a numeric value to put in for N. We're going to leave N as it is, and later on we'll let the limit do its course with N. Okay. But right now we have to hold on to N because we're not just dealing with 2, 3, or 4 rectangles. We're going to let that N push out to infinity. Okay, so we're just going to insert into the formula here. So B minus A over N. Let me just do this on the side here so we can kind of just save a step here. So B minus A over N, 2 minus a -2 over N. Okay, what does that equal to? 4 over N. Okay, so that's my width component. Again, it doesn't feel as nice as before because before we could just say, oh, the width is 2 or the width is 3, but now we have to hold on to that extra variable, 4 over N. So I'm going to just represent that width as 4 over N. That's the width component of each of my rectangle. And then here's my height components. F of A, what's my A value? -2. So we're starting at -2, and we're going to keep adding the width to reach the next subinterval. And that I is going to help it continually moving, right? So we did it all by hand, right? We did 0 plus pi over 8, plus pi over 8, plus pi over 8. And that's what that I is doing. It's going to keep adding the width to the next subinterval for us. Okay. Any questions with what this is doing here? Okay, so it's going to feel a lot more abstract because we're not seeing it play out. We have to kind of understand that we're dealing with infinite number of rectangles, so we don't want to be doing it all by hand. We want to just let the formula do its thing. Okay, so the next thing is we're going to have to plug this into the function, just like how we did before, right? We plugged 1 into x. Well, we plugged 0 in for x, pi over 8 in for x, but we used the calculator to do all that work. Here, we're going to just put this argument into the function and let that function kind of take its course. But we got to be able to know how to do this using this function notation. Okay, so let me just step off to the side and say, okay, here's my function. My function is 4 minus x squared. But we have to make sure that we are inserting the argument correctly into the function. Okay, and here is the way that we can do it without making a mistake. Go ahead and rewrite the function and leave a parentheses around every x that you see. Okay, if you can take this step, you're not going to make a mistake because you're going to have a set place reserved spot for this argument. Okay, so now we're going to take whatever you see inside the parentheses and insert it into the parentheses that you've created. All right. So if you can take this additional step, right? If you can do this, you're not going to make a mistake because you're going to know where to put that mess of an argument. Okay, are we good so far? All right, so now we have something that is related to the exact function we're dealing with. We're now gotten it out of function notation. So now we're going to take this piece and put it in for this function notation that we started off with. Okay. So the next step. So now we've entered into we've entered into the space that we started doing on Wednesday. Okay, so this is something that we did on Wednesday where we cleaned everything up, got all the i's resolved in terms of n, and then we found the limit as n approaching infinity. Okay, so now there's still a lot of messiness ahead of us, but we've had some exposure to how to do this type of problem, right? We did this on Wednesday, and that's what we're doing on Wednesday to try to get us ready to be able to handle these types of problems. Okay, so the work that's still ahead of us is we still have to FOIL this out. We still have to merge it with the 4. We got to multiply it by 4 over n, and then separate each of the subintervals, resolve all the i's in terms of n, and then within each of our subinterval or our fractions, we can evaluate the limit as it approaches infinity. Okay. So we want to make sure that we don't take a shortcut or the wrong shortcut with the exponent. We got to make sure we FOIL that out. So we'll write this out twice. So if I FOIL this out, I'm still going to leave it in a set of parentheses because after I FOIL this out, there's still that negative I still got to resolve. So I don't want to lose that negative or lose track of that negative. So I'm going to FOIL this out, but still leave it in one set of parentheses. So I get 4 minus 8i over n minus 8 over ni plus 16 over n squared I squared. Okay, so I'm just going to go ahead and distribute the negative through, combine the like terms, and see what we have. Okay, so I have 4 minus 4. This is minus 16 over ni with the negative in front, so it's going to give me positive 16 over ni, and then minus 16 over n squared I squared. What happens with that 4 minus 4? Just goes to 0. That's nice, but we still have that width component. We don't want to forget about that width component. That's still outside here. Distribute that 4 over n through. Okay, thankfully, we're down to 2 terms. We still have that sigma notation in front, so we want to separate into 2 sigma terms, and we want to begin separating what has impact from the summation rule and what doesn't have an impact. But I'm going to write this out twice. Separate my 2 terms here. What can we push out within the first fraction here? What's not part of my summation rule? 64 and the n squared. Yep, I can push that out in front. I can isolate my summation I and just refer to my summation I formula. Here with the second fraction, what can I push out? 64 and the n cubed, right? Okay. Okay, so we have a clean substitution for these 2 pieces. This is the n times n plus 1 over 2. And then I'm going to remember that ultimately I'm going to be finding the limit as n approaches infinity. So I'm going to be comparing degrees once I get this cleaned up. Minus 64 over n cubed. This is n times n plus 1 times 2n plus 1 all over 6. This one is not too bad to distribute. I'll go ahead and do all that. It's not too much work. But this, we prefer not to FOIL everything out, right? We talked about there's a bit of a shortcut, right? We only care about what's from the numerator. Yeah, we just care about the first term, right? The first term with the highest degree. And if I can just pick out each part and multiply that together, there are other parts to it, but we know that anything that has a lower degree is just not going to matter if we're doing approaching infinity, right? We only care about the highest degree. So if I multiply the 64, the n, and 2n, that gives me 128 n to what power? N to the third, right? Okay. There are other terms, dot, 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 but we don't have to spend the time to worry about that because we know that we have what we need to get our limit. Okay, so first fraction. We see matching degrees. Yes, right. And you know you're on the right track if every fraction is giving you matching degrees. Okay. Sometimes I see students realize that their degree is higher than the denominator. And the reason why I see students, most of the time that happens is because that is when we forget to include that with component. If you forget that with component, your degree is going to feel off. Okay. So don't forget about that with component because that is allowing your degrees to ultimately match at the end. So 64 over 2 is my resulting value. And then here, my degrees match as well. And I'm just going to take that 128 over 6. Use your calculator. Reduce that. 32 minus 128 over 6 is 32 over 3. So 32 over 3 is not only a approximation, it's the exact area. It does the work of using infinite number of rectangles to find the exact area under the curve. So we're starting with this concept of understanding that we're adding rectangles, okay? But we have a much more efficient way of working through this next week when we talk about power rule and first theorem of calculus, but that's also more abstract, okay? We lose the visual component of it, and it's good to understand this because we're going to have to need this later. But just let you know, once we arrive at this area, or once we learn this process, we're not going to have to do this every time moving forward. Okay, once we get past this quiz, we're largely going to leave this this formula behind and move on to a much more efficient way. All right. Any questions so far? Okay, I was going to want to start trapezoid rule, but this is kind of a small section. I'm going to save that for Monday. But I want us to do one more of this just so that we can get some more familiar, just get more familiar with this because there's so much going on here. So if you guys can turn to page 11. And we're going to work through number 1 together. Okay, I put the formula at the top of the page, and we're just going to kind of step through it together. All right, let's go ahead and find the width so that we don't have to put into the formula and we just kind of have it ready to go. Okay, what's the width going to be? 3 minus 1 over n, which is what? 2 over n. Yeah. So let's just go ahead and put 2 over n in for all the b minus a over n. And then we can begin to get that f parentheses into out of function notation. Okay, make sure that you include what can we replace with a 1. Okay, so f of 1 plus 2 over ni. So again, this is doing the job of inserting values into the function, but it's also incrementing to each of the subinterval values that we're going to be using. So our next job is trying to get this out of function notation so we can have something more, because right now we can't multiply these together, right? These are not compatible yet, but we do have a function that we're going to be using. So here's my function. Okay, so here's the foolproof way of making sure that we don't put that argument in the wrong place. We're going to rewrite this function and put parentheses, empty parentheses around all the what? All the x's. Yep. If you do that, you're not going to make a mistake because you're going to have very limited place to put that argument. So this is an important step here. If you can do this, you're not going to make a mistake with the argument. So now it's very obvious where the argument goes. It's going to go inside all the empty parentheses that you have set in place. So that 1 plus 2 over ni will go in for all these, for all those empty spaces. Okay, so now we're going to take all this that we created and insert it into replace this whole thing. Okay, so we're taking all this. This is my height component. My height component will replace my f parentheses, but I still make sure I don't want to forget my width component, right? My rectangle is width times height. So 2 over n is my width. This whole mess is my height. Okay, any questions so far? Okay, so now we have everything in the, we got everything that's compatible. So now we gotta just do the job of boiling this out, distributing the 2, distributing the 3, combine the like terms. And then don't forget, we gotta worry about getting that width component through as well. And then once we get all the parentheses resolved, we can start separating our terms and then resolving all the i's that still is not problem. I'm going to take the time to FOIL this out. So all this is still under my height component. I still haven't done anything with the width. I'm just quite trying to, I'm gonna try to clean all this up first, and then I'll work the width through. Combine my like terms here. 2 plus 2 is 4. 4 minus 3 is 1. The 8 over n squared I squared is its own thing. The 8 over ni minus 6 over ni is 2 over ni. Okay, so I've cleaned up my height component. I'm going to also involve my width component. So distribute that 2 over n through. Now things are becoming a little bit more familiar, right? I know I gotta separate each of them, let each be its own summation, pull out anything that's not part of my summation rule. So I got 16 over n cubed I squared, 4 over n squared times I plus 2 over n. Okay. Each of my terms will get its own summation. So then for my first term here, what can I push out in front? Yep, 16 over n cubed. Here I can push out what? 4 over n squared. Here I can push out 2 over n, but what's going to sit in place on the right side here? A 1. Good. Okay. I should be using I equals 1 to n, but I'm just kind of left it as it is. So we have a rule for summation I squared. We have a rule for summation I. We have a rule for summation 1. The goal is to get everything in terms of n so that we can just do limit as n approaches infinity with only one variable in front of us. Okay, so summation I squared is the n and n plus 1 to n plus 1 all over 6. Summation I is the n and n plus 1 over 2, and summation 1 is just the n. Okay, this is a mess, right? But we talked about how we don't have to worry about expanding all this out. We just have to take that first term from each part, multiply all that together, and that will produce the term that you need to get to your limit for this expression. So 16 times n times 2n gives us what? 32n to the third. That's a good degree because we see that degree below as well. So we know there's going to be a matching pair. Here, I'm just going to get 4n squared plus 4n. 4n squared is perfect because that's going to match my degree below. And then here, 2n over n is also good. We know. So every fraction, we should get a nice matching degree and pull out a nice fraction for each of my terms. Okay, so 32 over 6 is the result of my first fraction. 4 over 2, or 2, is the result of my second fraction. And 2 over 1, or 2, is a result of my third fraction. Add that together, 28 over 3. 28 over 3 represents the exact area under this curve between 1 and 3. Okay. Any questions? Okay, so your homework is just going to be from 4.2, 37 through 49. Don't worry about that trapezoid rule. 4.6, we'll fit that into Monday's notes. Okay, but I'll send out a reminder this weekend. Okay, go and get your phones.
So, right, did I do this for those? Yeah, and but then I'm not sure where, but like all my numbers. So got it. Okay.
Okay, here it's not 3.
Oh, it's not.
It's A. That A is 1.
You know,
But I mean, all your steps look
Right.
pretty good. I think just that 3 is missing.
yeah, all right, thank you.
Oh, and then the key is on the next page.
Same fact. Oh, that's like. But today it's one of the. Yeah. Yeah, I probably.
Because okay,
Wait,
yeah, so I think what happened is,
that's where my
see
sister.
that -3 there? That -3 is a -6 over.
Okay, so that applies to the whole thing.
Yeah.
Yeah, I
About a
think
6.
the goal split 6.
Thank you.
Yes, my grades are 7.
That's the max.
Yeah, wait, but my. I'll just let them bring my brother. I was like, and I have to watch him. I'll just like. Tell them to bring me up.
Well, we can give you a ride home.
Maybe.
Like if you, are you gonna drive there yourself?
Oh. I might just go through the apartments. I already worked on it.